The control room of the ESO Very Large Telescope at Paranal. Here, astronomers observe the sky using the advanced capabilities of this high-tech installation in the Chilean Atacama Desert. With great expertise, scientists and telescope operators master the VLT controls and make the difficult observations appear routine. But suddenly an alarm rings and calls for their undivided attention. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the ultimate frontier with our host Dr. J, aka Dr. Joe Liske.
Hello and welcome to the ESOcast. In this episode, we're going to learn about the Very Large Telescope's so-called rapid response mode. The point of this observing mode is to study gamma-ray bursts only a few short minutes after they are first spotted. Now, because the optical afterglow of a gamma-ray burst fades extremely rapidly, the observations must start as soon as possible after the initial discovery of the burst. And the VLT can deal with such time-critical observations better than any other telescope.
Gamma-ray bursts are the most powerful explosions in the universe. Astronomers do not fully understand their origin, but they are thought to be caused by incredibly energetic events such as the collapse of massive stars. Gamma-ray bursts are so energetic that for a brief instant they outshine the rest of their entire galaxy. They produce more energy in a few seconds than the Sun will in its whole lifetime. After the flash of gamma rays has ended, an optical afterglow can usually be detected for a few hours. Astronomers look at this to learn more about how and why gamma-ray bursts occur. Because gamma-ray bursts typically occur at a very large distance from Earth, their afterglow is faint. In addition, the afterglow fades very rapidly, so that within a few hours it can be up to 500 times. In order to learn more about the nature of a gamma-ray burst and the influence of the explosion on its surroundings, the event must be observed as quickly as possible.
Now, the VLT is perfectly equipped to obtain high-resolution observations of a gamma-ray burst. But before it can do so, the burst must first be discovered. The SWIFT satellite chases gamma-ray bursts with its wide-field Burst Alert telescope. Once a burst has been discovered and verified, it is immediately reported to the VLT and other observatories.
An alarm at the VLT console indicates to the astronomers that the activation of the rapid response mode has been requested. The scientists have to confirm that the VLT unit telescope can be moved safely, and within seconds all ongoing observations are stopped. Then the system performs robotic observations without any human intervention, except the automated procedure guarantees quick and accurate observations. In fact, the VLT allows astronomers to begin observations within only a few minutes of detection by SWIFT. With events as short-lived as these, this can mean the difference between making high-quality observations and seeing nothing at all.
But the VLT at the Paranal Observatory is not the only ESO facility which carries out gamma-ray burst observations. At the Silla Observatory, there are also telescopes that can observe these events. The 2.2-meter MPG ESO telescope features the GROND instrument, which takes images of the afterglow simultaneously in 7 different colors. And that gives astronomers further insights into the physics of gamma-ray bursts. In addition, there are 2 smaller telescopes, the 60cm REM and the 25cm Tarot, and these are also located at Silla. These robotic telescopes are designed to react immediately when they receive an alert on a gamma-ray burst, making it possible to start observing the burst within seconds.
Scientists agree that gamma-ray bursts are associated with the formation of black holes, but until now the exact nature of the bursts remains enigmatic, and more high-resolution spectroscopy data is needed. The VLT offers enormous light-collecting power and high resolution. In addition, it is equipped with a suite of high-tech instruments. It is the combination of the VLT's enormous observational potential with ultra-fast response times, which provides data of superb quality to the scientists who study gamma-ray bursts.
The rapid response mode at the VLT will be triggered many more times in the future, and ESA will continue to collect first-class data on gamma-ray bursts. Data which will perhaps one day help to unravel the secrets of the most energetic explosions in the universe. This is Dr. J, signing off for the ESOcast. Join me again next time for another cosmic
An
adventure.
exoplanet orbiting a star that entered our Milky Way from another galaxy has been detected by a European team of astronomers. The Jupiter-like planet is particularly unusual as it is orbiting a star nearing the end of its life and could be about to be engulfed by it, giving tantalizing clues about the fate of our own planetary system in the distant future. Hello and welcome to the ESOcast. In this episode, we're going to find out how an act of galactic cannibalism has brought a planet from another galaxy within astronomers' reach. Astronomers have detected nearly 500 planets orbiting stars in our cosmic neighborhood, but none outside our Milky Way has been confirmed. Now, however, a planet weighing at least 1.25 times as much as Jupiter has been discovered orbiting a star of extragalactic origin, even though the star now finds itself within our own galaxy. The star, which is known as HIP 13044, lies about 2,000 light-years from Earth and is part of the so-called Helmi stream. This stream of stars originally belonged to a dwarf galaxy, which was devoured by our Milky Way in an act of galactic cannibalism 6 to 9 billion years ago. Astronomers detected the planet by looking for tiny, telltale wobbles of the star, caused by the gravitational size observations. The team used a high-resolution spectrograph called FAROS, attached to the 2.2-meter telescope at ESA's La Silla Observatory in Chile. The planet, HIP 13044b, is also one of the few exoplanets known to have survived its host star massively growing in size after exhausting the hydrogen fuel supply in its core, i.e. the red giant phase of stellar evolution. HIP 13044b is near to its host star. At the closest point in its elliptical orbit, it is less than 1 stellar diameter from the surface of the star, or only about 0.055 times the Sun-Earth distance, and it completes an orbit in only about 16 days. The astronomers hypothesize that the planet's orbit might initially have been much larger, but that it moved inwards during the red giant phase. Any closer-in planets may not have been so lucky. Astronomers suggest that some inner planets may have been swallowed by the star during its red giant phase. Although the Jupiter-like exoplanet has escaped the fate of these inner planets so far, the star will expand again in the next stage of its evolution. When this happens, the star may engulf the planet, meaning it may be doomed after all. The astronomers are now searching for more planets around stars near the end of their lives. Their work may tell us about the distant fate of the planets in our own solar system, as the Sun is also expected to become a red giant in about 5 billion years. This is Dr. J, signing off for the ESOcast. Join me again next time for another cosmic adventure.